All right, so today we're going to be looking at number systems and ordering. So what are number systems? You've been dealing with this since kindergarten. The very first thing you had to do going into kindergarten is you had to know your counting numbers. 1, 2, 3, 4, 5. Well, that's a system, okay? That is a numbering group. And so we're going to look at all those different ones that you've learned growing up, from kindergarten on up, and show you how they are nested together in the numbering systems that come after that, okay? Or the number groups that come after that. So counting numbers was the first one. Then they throw in 0. When you throw in 0, that is your whole numbers. So you have the whole numbers. These are 0. Let me put it differently. 0, and then the counting. Okay, whole numbers. So that's the smallest group after counting. The next thing you did along the way at some point, maybe not in the same order in which you learned it all, but one of the groups that came later is the integers. You might have started experiencing this somewhere right around maybe 6th, 7th grade. What are the integers? Well, the integers are the whole numbers and then the negative versions of those also. So you have 1, 2, and 3 forever, and then on this side, -1, -2, and so forth, all the way down to forever in that direction. Integers. So in the nesting system of that, every whole number is also an integer, right? Every integer is not a whole number. Only some of them are whole numbers, but every whole number is an integer. So over here, the whole numbers are inside integers. So you have integers that are not whole numbers, and whole numbers are also integers. Another numbering system that you had, or group that you had, you called it something different at the time you learned it, but they are called rational numbers. Rational numbers. You are more familiar with them as fractions. Okay? But they're actually called rational numbers. And here's the definition of a rational number. So this is how you know if it's a rational number or not. Because there are rational numbers that don't look like fractions. Okay? And so here's one definition. It's any number that can be written in the form P over Q. So in a fraction form. So is 3 a rational number? Yes. If I write 3 as a fraction, it would be 3 over 1. That is a fraction form, so 3 is a rational number. In fact, every whole number is a rational number. Every integer is a rational number. Every fraction you can think of is a rational number, but yet there is even more than those. Okay? So another way to look at it that might be helpful also is you can look at it in a decimal setting or mindset. A rational number is a terminating or repeating decimal. Terminating means that it will end. So if I write a decimal number, 0.1239652197255, and I stop saying the numbers, I just described a rational number because that can be written as a fraction. A repeating decimal would be one that looks like something that can do this. 0.3333333333333 and all the way forever is 3. Okay? That is also can be written in fraction form. I'll show you how to do that some other day. And that is a rational number. So anything that you can write as a fraction in a fraction form is a rational number. Or you can look at it as a decimal. Anything that terminates or repeats is also a rational number. So all whole numbers are rational. All integers are rational, which means these two are nested inside of rationals. rational numbers are numbers that terminate or repeat. What's an irrational number? Well, what does the word irrational mean? It's not rational. So any number that can't be written as a fraction, or any number that is in a decimal that never stops and never repeats, would be considered an irrational number. So what are irrational numbers? Numbers that are not rational. So we just piggyback off of that definition. Okay? So if it's not rational, then it's irrational. And the irrational numbers, there is no overlap. You can't be rational and irrational at the same time. So they are separate groups. There is no overlap whatsoever at any time. So irrational numbers are next to rational numbers. Which leads me to the next group that we use, which is called the reals. Real numbers are all rational and irrational numbers. So in other words, both of these together are the reals. Both sets, all of these numbers, anything that can fit into this box is a real number. You are familiar with these real numbers because how many times, if you've ever written a number line, every time you write a number line, you are writing what's called a real number line. That's what it is. Okay? If I draw this line right here, that you're probably familiar with, arrows on both ends, and we put little tick marks here every once in a while. We usually put 0 here and maybe do 1, and see how we're marking really kind of like the integers, aren't we? As placeholders. Here's -2, -3. But see, I didn't just identify, I've only put these marks as little spacers. Every single real number is on this line. If I needed to, I can find out where, well, where's 1/2? Well, 1/2 is between 0 and 1 right in the middle. So there's a little dust particle right here that represents 1/2. If I wanted to express it, I could put a little mark here in the middle and put the fraction 1/2 underneath it. So this number line is a number, a line that represents every single real number. Okay? And what's interesting about it is this arrow means it goes on forever in a positive sense, and this arrow here means it goes on forever in a negative sense. Okay? This goes on forever. And it's kind of like a mirror image of each other. So whatever's over here is positive. There's a negative version over there also. Okay? Now, there's more. What? There is. You may not explore it too much in this class. I don't know if we do or not. I can't remember. But in Algebra 2, you'll explore the next numbering group that's bigger than this one. Okay? And without giving too much information about it, because we're really not going to deal with it in here for at all or for a very, very, very long time, you need to know that it does exist. Okay? And that is this. It's called the complex numbers. Okay? And again, other than the definition I'm going to give you, don't worry about this one too much. If you don't remember it, don't worry about it. I'm not going to stress about complex numbers. Your world exists all the way up to the reals. Okay? That's what the real numbers means. It's the real numbers that you're familiar with in the real world. Okay? Complex numbers are important, and I'll explain to you why in just a minute here. Let me write out what it is. It's a number of the form, and it looks like this, a plus bi. So that's the number where a and b are real, and I is the square root of a -1. And that's really what kind of blows everything out. So how do I do a square root of a -1? Okay, don't worry about it. I will explain all that in a later date. Okay, I'm just telling you that there's something bigger than reals. There's something bigger than reals. So in the big scheme of things, everything in here, everything, every single real number is also a complex number. But there are numbers that are not reals that are complex. It's a bigger system. You don't need to worry about it too much, but that's how that works. Okay? These are your number groups. This is the smallest one. Every whole number is an integer. Every whole number is irrational. Every whole number is not irrational, because you can't be both. Okay, so if it's irrational, it cannot be irrational. Every whole number is real. Every whole number is complex. See how this works? So, what are some irrational ones? This one causes a lot of confusion. People don't really understand what I mean by that. Well, there's a number that's irrational that you might be familiar with. It's kind of famous, called pi. Have you ever heard of it? Right? But usually they do an abbreviation for it, like 3.14, right? It's what we kind of use on a calculator and stuff like that. Well, that's not the actual number. You know that, right? Pi is a number. It's a decimal number that just keeps on going forever. It goes on forever, never stops, never repeats. Okay? So that is a irrational number. So an example of an irrational number would be pi. Is one example. Okay? And then you ask some people, well, what's another one? And then people start, I don't know. Right? You can find a gazillion number of rational numbers, but it's really hard to find an irrational one other than pi for you right now. Well, there are other ones. I'll go and give you a hint right now. There's another number you're going to learn at a later date, usually in Algebra 2, and it's called e. It is also an irrational number. It's a famous number. It's like pi, right? But you'll talk about that one in Algebra 2, not here. But here's one that you might be familiar with. Do you kind of understand square roots? A square root, okay? Like the square root of 4 would be 2, kind of a thing. Do you know that there's a square root of 2? So you all know the symbol square root? Well, the square root of 2 is also irrational. In fact, the square root of every single number that you don't know the square root of, that aren't what's called perfect squares, are irrational. So like the square root of 3 would be in here. The square root of 4 we know is 2, right? So the square root of 4 would not be an irrational number because the square root of 4 is 2, and 2 is a rational number. See, that's what I was talking about. But can you take the square root of 5? Do you know it? Square root of 5 is irrational. The next square root number that you know would be 9, wouldn't it? The square root of 9 is 3. Everybody agree? So everything between 4 and 9, so the square root of 5, the square root of 6, the square root of 7, the square root of 8, those are all irrational numbers. See, so now you can come up with a bunch of them, can't you? So there's an infinite number of irrational numbers. There's a bunch of them. These are just a few examples of them. Okay? So let's go back to this number line right here. In this number line right here, we're going to start looking at what's called ordering. So you got to make sure you understand how this works. This is a real number line. There's more numbers here than that you see. Is 1 million on this number line? Yes. Do you see 1 million on this number line? No. But it's there, isn't it? It's out here on this arrow. Every number is on here. When you draw it, you're representing every number, even the ones you don't see. As you go in this direction to the right, the numbers get bigger. As you move to the right, the numbers get bigger. So one of the things you need to be able to do is to find out where these numbers are in various forms on a number line. How do I put the numbers in order? Where are they? If I ask you to find where a number is, okay, can we place it in here in a fashion? Well, first off, remember, all the negatives are on the left, right? -3 is smaller than -2 because as I go to the right, the numbers get bigger, correct? So even though we think 3 is bigger than 2, but -3 is actually smaller than -2. All right? So that helps you place things. Negatives on this side of 0. Fractions usually end up between numbers, correct? All right. How can I compare numbers? How do I know when one number is bigger than another one? We'll talk about this a bit too. To compare numbers, put them in the same form. In other words, put them all as fractions or all as decimals. All fractions are all decimals, okay? It's really hard to compare a fraction with a decimal. Weird ones. I mean, there's some common ones we can kind of tell the difference on, but I mean, like, which one's bigger? 1/3 or, 0.3196215. See, one's a fraction, one's a decimal. It's kind of sometimes hard to tell. That was kind of an easy one because of certain issues, but you get my point, right? I mean, there's some fractions and some things I can make so close that you'd be hard to tell. So make them the same. Either make them all fractions or make them all decimals. A lot of times the decimal is the easier route, just so you know. The decimal is sometimes easier. So that's how we do comparing. The other one we want to look at is approximating, like, well, how about a square root? Okay, what about a square root? I'll put an example in here. Where would a square root of 19 go? I mean, which one's bigger? Is the square root of 19 bigger than 5? Is it less than 5? Is it bigger than 10? Is it less than 10? Do you know? Can you use a calculator? So how can I go about doing this? Can I figure out a way to kind of get an idea of what this is? And I'm going to show you that right now. That's kind of cool. All right. Well, this is a square root. Okay. It's a square root. And so when you deal with square roots, you want to think of perfect squares. So what is a perfect square? Perfect squares are 1, 4, 9, 16, 25, and so on. And why are these numbers perfect squares? Because they all come from the fact that this is 1 squared, 2 squared, 3 squared, and hopefully you kind of see what's going on now. So they're called perfect squares because they are numbers that come from squaring an integer. Perfect square. These are also the numbers that you actually know the square root of. For example, if I take the square root of 9, we know the answer is going to be 3. If I take the square root of 16, the answer is going to be 4. Right? We just talked about that just a moment ago. So where is the square root of 19? Well, what I want you to do is I want you to come over here and look for the perfect square, that one smaller and one bigger than 19. So 19 is between 16 and 25, isn't it? So mathematically, I can write that as 16 is less than the square root of 19. Excuse me, is less than 19, which is less than 25. Well, that's not a 19. That's the square root of 19, correct? But since 19 is between these numbers, if I square root everything, then the square root of 19 is between the square root of 16 and the square root of 25. It has to be. Okay? And the square root of 16 is what? 4. So the square root of 19 is between 4 and 5. Did you ever see that? So if I was graphing, if I had to graph the square root of 19, I can do this little technique and get a ballpark about where it's at. Okay. Now I can go one step farther here. Now let me ask you another question. This is 16, that's 25. Where is 19? Is it closer to 16 or is it closer to 25? It's actually closer to 16, isn't it? It's 3 away from 16, and it's what? 6 away from 25, right? So it's 3 in one direction, 6 in the other direction, right? So what decimal would you ballpark that at? I mean, it's less than halfway, isn't it? Between them, right? So then my answer has to be less than 4.5, doesn't it? So what would you guess it at? Is it close to the middle? Close to the 16? Close, you know what I'm saying? So this is how you can kind of estimate or ballpark where you're at. So I can estimate that the square root of 19 is probably less than 4.5. So what's kind of between 4 and 4.5? 4.2, 4.3? I like 4.3 a little bit better, just because it's not really halfway to halfway, so it's a little bit more than that. So I'm going to go a little bit bigger there. And so let's find out. My calculator over there. I don't want you guys to get up and do anything. So where's my square root button? Right up there. So I type in 19 and the square root. Boom, boom. There it is. That's square root of 19. I estimated it at 4.3. What is it at? 4.35, such and such, right? So I was pretty darn close with that. Close enough for what we're doing here to find out where it goes. That's what we're looking for. So my approximation, 4.3 without a calculator, was pretty close. So these are some of the things you're going to be doing in your homework assignment today in just a moment. Some rules I want you to know that will also help you with simplifying some radicals. And we'll explore this in a little bit more detail as we move along through this class. Okay? So here's some rules to know about square roots. If I have a square root and a product underneath it, I can split the square root like that. And if I have it in a fraction form like this, I can take the square root of the top and I can take the square root of the bottom. Again, we don't know how we're going to use this yet. It's just something to identify and know right now. And we're going to do some problems and some examples and some questions I'll take out of the video.